Hi, I am Neelu, and I'm excited to present our work on CL-MAE, Curriculum Learned Mask Autoencoders, co-authored by Cătălin and myself. This research is a collaborative effort with our awesome supervisors Kamal, Thomas, and Radu. In this paper, we present a novel approach to self-supervised representation learning, which is a powerful technique for acquiring a generic representation of data while solving a self-supervised pretext task. Mask autoencoders are a popular approach that learns such a scalable generic representation by reconstructing mask token from an image. Our approach is based on MAE. However, unlike random masking as used in the MAE, we proposed an intelligent masking scheme using curriculum learning. Our main contribution in this work are: first, we introduce a curriculum learning into MAE framework. The curriculum in this case is constructed by generating masks of varying complexity. We then propose a novel curriculum masking module, which is capable of generating these masks adaptively. Finally, we integrate our curriculum learning framework with MAE. We compare our method against vanilla MAE on 5 downstream tasks and observe that our method curriculum learned MAE outperforms the vanilla MAE by a significant margin on each downstream task. Let us first understand how MAE works. Given an input image, we randomly mask 75% of the total patches. We only provide visible patches to the encoder network. After encoding the visible patches, we add mask token along with the encoded representation. Finally, we reconstruct the mask patches. In this way, we learn a generic representation. Mask autoencoders are based on random masking. We, on the other hand, propose an intelligent masking strategy using curriculum learning, where we increase the complexity of mask from easy to hard as the training progresses. To obtain such mask, we propose a curriculum masking module. Now let's take a look into our curriculum masking module. Given an input image, we first break down input image into fixed size, non-overlapping patches and generate their corresponding patch embeddings. Now we add 5 self-attention blocks into our curriculum masking module. The number of self-attention blocks is a hyperparameter in this case, which we decide based on our experiments. Finally, we extract the class token, which contains the information about the entire image. We use this class token to generate the masking output. Our curriculum masking module generates a decisive masking output such that the visible token are pushed towards the value 1 and the mask token are pushed towards value 0. We then unpatchify the masking output to generate our output mask. The output mask now has the same size as our input image. We binarize the output mask by using a thresholding operator. This binarized output mask is used in the selection of visible token from the input image. Once we select visible tokens, they are now provided to the MAE for the representation learning. We observe that the thresholding operator after curriculum masking module inhibits the gradient propagation. Therefore, we propose two-step training in our method. In step 1, we use the thresholding operation and train MAE for representation learning. Our curriculum masking module is kept frozen in this step. In step 2, we remove the thresholding operator and train our curriculum masking module, and we keep MAE frozen in this step. We propose total 4 loss functions for the training of the novel curriculum masking module. Curriculum loss, which is included to generate adaptive mask. These adaptive masks are modified during the training progress such that it increases the complexity of the pretext task. Gaussian loss, which ensures a decisive masking, where patches with a value close to 1 are visible and the patches with a value close to 0 are masked. KL divergence loss, as shown in the top left figure, model learns to mask everything to increase the complexity of the pretext task, including KL divergence loss, ensure our desired masking ratio. In our experiments, we keep the desired masking ratio same as MAE, which is 75%. Our final loss function, diversity loss, ensures diversity among the generated masks. The bottom left figure compares the generated mask from 2 samples with and without including the diversity loss. We can see here that these masks show higher variance after including the diversity loss. We train our curriculum masking module with the combined loss obtained by adding these 4 loss functions. For evaluation, we integrate our curriculum learning approach with 3 different width architecture: width base, width large, and width huge, and compare our method against vanilla MAE using top 1 and top 5 accuracy. In our experiment, we performed classification tasks on 5 downstream datasets: aerial images, Airbus wind turbines, architectural heritage elements, sea animals, and sport balls, and evaluate the results under 3 different scenarios: nearest neighbor, linear probing, and few shot linear probing for each dataset. These are some quantitative results. Top 3 rows compare the classification result using nearest neighbor algorithm on 5 different downstream datasets. The last 3 rows presents a classification result using linear probing technique. We observe significant improvement in almost all cases. The graph here shows a result from our few shot experiments on 3 different datasets: aerial images, Airbus wind turbines, and architectural heritage element. We compare 1, 2, 4, 8, and 16 shot linear probing results here. The orange curve in the graph represents CL-MAE, whereas the blue curve represents vanilla MAE. We observe that our method outperforms vanilla MAE in each case. These are the few shot linear probing experiments on sea animals and sport balls datasets. We observe the similar improvement here as well. We show the evolution of our generated mask over the training. The first row is our input image. The second row shows a generated mask, where the curriculum masking module is trained with a consensual objective in order to make the pretext task easier. We see here that the model learns to retain more token from the foreground while masking the background tokens. The last row in this image shows the adversarial masking, where the curriculum masking module learns to increase the complexity of the pretext task. We observe that the learned mask retains the background while masking majority of foreground tokens. To conclude, we propose a novel approach for self-supervised representation learning based on curriculum learning. We propose a novel curriculum masking module which has the capability to generate the mask adaptively. We propose 4 loss functions for the training of our curriculum masking module. Finally, we observe from our empirical results that curriculum learned MAE outperforms the baseline vanilla MAE on multiple downstream tasks. Thank you for listening. Our code is available publicly on GitHub.